Let me start this.
Okay.
Perfect. It's recording. So thanks everybody for coming today. This is Guilherme Paiva. It's a postdoctoral researcher in the Center of Computer Music Group of the University of São Paulo. He did his PhD in the Laboratory of Acoustics of Le Mans. Some of you may know, or may have applied for a PhD there too. And he researched on physical models of musical instrument sound system. He also did a visit in YAMAHA where he met Hannah, who introduced him to me, and the co-founder of a startup, Turbonius, which works in the development of computational platform for musical instruments and room acoustic simulations. I think it's a very nice fit to what we do here in the lab, and the floor is yours. You can start whenever you want. I'm just gonna mute myself now. And do you want questions during the talk or at the end?
Sorry?
Do you want the questions during your talk or at the end?
During, as you want, during or in the end. For me,
Okay,
when you have
perfect.
questions, for me, it's okay.
If you have any
So,
questions, just interrupt. You can use the
okay,
chat or...
you can interrupt me. Yeah, okay. So thank you, Sebastian. Thank you, Cremona Lab. It's a pleasure to be here today to talk about my little experience in physical modeling and sound synthesis of string musical instruments, okay? So I think an important question, a first important question here, is why modeling and synthesizing musical instruments, okay? So there are many reasons for that. In my case, since my PhD, I've been involved in several projects linked to the development of decision support tools for instrument makers, okay? So we used these physical models as prediction tools, okay? In order to support the innovation and the improvement of these musical instruments by avoiding trial and error methods. So we could save money, materials, okay, time, and we can optimize in this manufacturing process, okay. So in the first part of this presentation, I will show you some results of the study of the viola caipira. This is the work that resulted from my PhD, okay? So we performed experimental procedures in this study to identify acoustical and vibrational specificities of the viola, okay? And we also developed a sound synthesis model, and this sound synthesis model was able to reproduce the instrument's specificities that we identified experimentally, okay? And the second part, which is my current project, my current research, in my postdoctoral research, okay, address the influence of the material properties uncertainties, okay, in the sound production. So I will show you a sound synthesis framework that we developed, and this framework was able to include the materials uncertainties, okay, and using this framework, we performed numerical investigations to study the uncertainties effects on the sound synthesis, okay. So the viola caipira. What is a viola caipira, okay? I think it's important question mainly here. So it's a typical Brazilian guitar, you can say, okay? The viola is little studied in musical acoustics. So, but not every Brazilian guitar is a viola caipira. It's important to say that we can find Brazilian guitars with different geometries, different materials, string arrangements, tuning types. As you can see here, we have 5 examples of different Brazilian guitars. Okay, and even if we consider the viola caipira, we can find a lot of difference. Okay, it's a diversified instrument, so you can find different configurations. So, but we needed to define an instrument to investigate. Okay, so
Can I interrupt?
consider. Sorry.
Right.
Okay. Of course. Of course.
The materials, I mean, I imagine the top to be a spruce, it looks like, and the bottom would be like tropical hardwoods from Brazil, no?
Yes. 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 This is a hollow from a coco. It's like a coconut hollow. It's extracted from the coconut. Yeah, we have different materials here, but actually we still use, although we have a lot of different woods here, good and suitable woods for musical instruments, we still use the traditional ones, yeah, the European woods, a bit spruce stone woods, mahogany, and Indian rosewood. Okay, so this is a important question to how to use these tropical woods to manufacturing musical instruments. So continuing, we considered the most popular type of the viola caipira, okay, which is this one. I'm gonna show you a short demonstration. It has 10 strings, okay, arranged in 5 pairs. The 3 upper strings, the upper pairs, are tuned in octave, and the two lower pairs are tuned in unison. Okay, so some results from the experimental study. Okay, in the first part of this experimental study, we used the high-speed camera to analyze the string motions of the viola caipira during different plucks. Okay, so in this first video that we obtained, the typical pluck of a string pair is analyzed, okay, at which we can note a particular double pluck. Okay, I'm gonna play it. So the first pluck, this first string is plucked, the second string is plucked at 40 milliseconds. We can note also the non-planar motions of strings. And finally, the string-string collisions, okay? So this is an important phenomenon that it's an important phenomenon that influence the sound of the instrument, okay? So in the second video, a single pair of the viola caipira is plucked. So we can note also that the other strings vibrate. These are sympathetic resonance, okay, which is due the energy transfer through the bridge, okay. And in the second part of this experimental study consisted of recording 2 sounds, okay. The first sound, we damped all the other 9 strings, so just one string is free to vibrate. And the second sound, all the strings are free to vibrate, okay. So you're gonna listen the 2 sounds, one after the other, first the 1 free string and then the 10 free strings, twice, okay. I recommend to use phones or at least a good loudspeaker, and if you can turn up the volume to be able to perceive the difference, because they are very subtle, okay. So okay, I'm gonna play it. So I could perceive a difference between these 2 sounds. We calculate the respective spectrograms from these 2 sounds, okay? Considering the 1 free string configuration, we can note beating phenomena, okay, associated to the 2 orthogonal transverse motions of the of the strings, okay? And if we consider both spectrograms and look at the second partial, for example, in the 10 free strings config, we can note some beating, yeah, here. And this is due to the interaction of the multiple strings of the partial of multiple strings, okay? So we can note this phenomenon here. In addition, we can also note the augmentation of the decay of some partials here, if we compare, okay? This phenomenon is called sound halo, okay, sound halo, and it's due to the string sympathetic vibrations, okay, of the fully coupled system. And so I will present you the main aspects of the physical model that we developed. If you want to know more about this model, you can find a complete description in this JSV paper that we published in 2019, okay? And do not hesitate to ask me here in this presentation, okay? Feel free. So we developed a physical model that used a hybrid model approach, okay? It is model based because it starts from the modes of the uncoupled strings and the modes of the uncoupled body. I mean, the model is fed by the modes of the uncoupled string and the modes of the uncoupled body. So it is hybrid because the string modes here, they are determined from analytical expressions, okay? So they are fixed. And the body modes, we can obtain them from an experimental model analysis or a numerical model analysis, okay? And for the string modes, we consider the model basis, the modes associated to the string with pinned ends here, okay? Plus an interface mode. This interface mode, it's the mode associated when the string is pinned in one end and at the other end is loaded, okay, here. So how can we couple these two structures, string and body? We consider a coupling force acting at the string body coupling point, okay? So we have a pair of action and reaction force, okay, represented here by the vector Fc in time. And this vector is unknown, okay? We don't know the value of this vector in the initial stage. So we use a finite difference temporal scheme, okay, to compute this coupling force. So how did we do that? At a given time step e+1, we impose a kinematic coupling at the coupling point, so we can compute in the previous time step the coupling force Fc, okay? Basically, this is the principle of the method, okay? So as we identified collisions between strings, we should be able to include this phenomenon in our model, okay? So we know that collisions are everywhere in musical instruments, okay? In all the types of instruments, and including the viola caipira, okay? So to include these string collisions, we consider first, we need to consider this formulation here. We first consider the cross sections of two collide strings, okay? So we can define the interpenetration represented by delta here and the impact force, okay, at these cross sections. So we used a nonlinear model with hysteresis damping by Hunt and Crosley, which is a model for contact, okay, a contact force. And in this model, takes into account the interpenetration, okay, the contact stiffness, the compliance exponent, and the damping coefficient. So we performed some numerical experiments. Here I will show you some results, okay? In the first experiment, we consider a single string pair, okay? So we plug as a single string, D3, so we can observe the collisions, okay? In time and space here, given in this diagram, which we called collision space-time diagram. Here we have the string length, okay? Here in time, and this axis is the time. So each black point here is corresponds to a contact point between the two strings, okay? So in this diagram, we can see that the moving contact point is repeated several times with ever shorter durations involving ever smaller portions of this string, okay? And we can, another important result here, that this collisions occurs in the immediate transient phase, okay, just after the pluck. So considering the same configuration, I mean, a single string pair, we simulated two sounds. The first sound, do not consider collision, okay? And the second sound considers collision, okay? So I'm gonna play one after the other, first without collision, then with collision twice, okay? Okay, so we obtained the respective spectrograms. So from these spectrograms, by comparing both spectrograms, we can, and by comparing the two sounds, for me, I could perceive bzz, like a sound bzz in the just beginning, okay? So we call the buzzing effect, which is induced by the repeated collisions in the early transient phase, okay? And from this spectrogram, and by comparing them, we can see the spectral rays are broadened during the collisions, okay? And we can also note the redistribution of the spectral components, mainly in the high frequency components here, okay? This is another effect originated from the collisions. So we simulated the fully coupled system considering the 10 strings, okay? In this numerical experiment, we plug a string parallel to the soundboard, the D3 string, and we can note sympathetic resonance as we had identified experimentally.
So here you are simulating just the bridge and not the top plate.
No, actually it's the bridge and the top plate, but in this video we just we show only the strings, but they are coupled to the top plate, okay?
Okay.
And in this work, as I said, we can extract the body modes from numerical or experimental mode analysis. For the viola caipira, we measured a real viola, so we extract experimental modes, and and we could include this real viola in our simulation, okay? So this is the complete instrument, okay? So we could note sympathetic resonance, and we generated 3 sounds, okay? We're gonna listen first a single string without 10 strings, okay? The second sound, we consider the 10 strings, but without collisions. And the third sound, we consider the 10 strings, but with collisions. So let's see if we can perceive the difference. I'm gonna play these three sounds one after the other twice, okay? Okay. So, okay. So now we performed a more realistic condition, yeah, for simulation. So we can play all the strings, we can play chords. So this is a sample, a demonstration of a more realistic simulation, okay, of the synthesized viola caipira. So to conclude this first part, we could identify the specificities of the viola, okay? Specificities are a particular double plug, sympathetic resonance and beating phenomena, collisions between strings, okay? I showed you a physical model that we developed, including the string collisions, and this model was able to reproduce the main features of the viola caipira. And we also identified the collision effects, which are Bising, spectral enrichment, and the redistribution of the spectral components, okay? So let's go to the second part of this presentation. This part addresses the uncertainties in wood mechanical properties and their impacts on the sound. Actually, this research is in initial phase, okay? So we have more time to develop. We still have a long time here to develop this topic. So an important point here is the woods, as we know, show a high variability in mechanical properties, yeah, between species, subspecies, individuals, and even if we consider the same individual. So the question is, what are the impacts of the wood mechanical properties uncertainties on the sound production? Okay, so here we propose to perform a numerical investigation, okay, to study the uncertainties effects on the sound synthesis. So we're gonna use the sound synthesis of a simplified string instrument, okay. So we used the sound synthesis that we developed for the viola caipira, but we had to adapt it. And as I mentioned, now we extract the body modes from a numerical modal analysis. In the previous work, we extracted from experimental modal analysis, okay? So the simplified instrument we called a square plate guitar, okay? It consists of a square soundboard coupled to a single string, okay? It's a G3 string. The sides of the soundboard of this guitar have 0.5 meters and its thickness is 3 millimeters, okay? The soundboard is made of spruce stone wood. The string is always plucked in the same condition, I mean at 15 centimeters from the coupling point. So we could obtain singletons of 8 seconds of duration. And we consider the string and body modes up to 2000 hertz, okay? So, so we should perform a numerical model analysis using a finite element method, the finite element method, okay? So we consider the orthotropy of the wood. We need to consider 10 properties, okay, to describe the mechanical behavior of the soundboard plate. And in order to include the uncertainties in the material, the elasticity moduli EL and ER and the shear modulus GLR are assumed to be stochastic variables, okay? And these variables are defined as uniform distributions between upper and lower limits, okay? These upper and lower limits we're calculating by considering plus and minus 10% of the nominal value, which are shown here, okay? And why did I choose only these 3 properties, okay? This choice is based actually on previous sensitivity analysis presented by Viola and co-authors, okay, which showed that the most influential parameters on the dynamic behavior of tonewood of a spruce plate, okay, are these 3 parameters, okay. So we consider just the uncertainties of these 3 parameters. So so if we want to consider these uncertainties, okay, and we need to perform a stochastic finite element analysis of the body, okay. So we used the Monte Carlo sampling method, which allowed to generate a set of body model bases, okay. So we applied random variations to the 3 stochastic variables, to the 3 properties, okay, the wood properties. So we could obtain 300 simulations, okay? I mean 300 model bases, body model base. And we used this body model base to fit our sound synthesis method. So in the end, we obtained 300 random sounds, okay? First, starting from a deterministic approach, I mean, from the nominal values of the wood properties, I can obtain a single sound, okay? And from the single sound, I can compute the sound magnitude spectrum, okay? Which is represented here. And in this sound magnitude spectrum, we can identify the string mode contributions, okay? Harmonic comp of equally spaced peaks with a fundamental frequency at 196 hertz. And we can also identify the body mode contributions, which is a group of less prominent resonance peaks with distinct space and magnitudes, okay? So considering those 300 sounds, 300 random sounds, and gathering all the respective spectra and superposing in the same figure, we obtained this representation here, okay? From which we can see that the body mechanical properties uncertainty leads to a significant dispersion of the sound magnitude spectrum, okay? We can note, of course, this expression is more visible in the regions of body mode contributions because these properties, only the properties of the body consider the uncertainties, okay? While the string mode contributions remain without significant dispersion, okay?
One question.
Oh, of course. Oh, sorry, I didn't see your that you up with your hand.
Yeah. The variation in the frequency of the first mode, like how much it is.
Oh, how much? I don't know exactly, but I can say that I remember it's the frequency value. It's about 0.5 hertz or 1 hertz. I mean, no, sorry. I'm considering the fundamental frequency of string. I don't know exactly, but I can find this information. Okay. I
Because
have the results.
we do the same for like the violin plate, and when we superimpose, the peaks get a bit wider, and there is a
Okay.
significant shift in frequency.
Ah,
But
yes.
and how much was the spread of the variation in the stiffness? I lost that part.
The stiffness.
The spread in the variation, how much plus minus how much percent?
10%.
Okay, yeah.
10,
That's the same
plus
we
and
do.
minus 10%. Okay, of the mean, the nominal value.
Yes.
Okay.
Yes.
Actually, yeah, it's a parametric approach. Yeah, but now we are generating some simulations considering the experimental spread. Okay. So gathering all these curves, okay, we could perform the statistical moments of these curves. Here we can see in red, it's the mean spectrum, okay? And this blue region is centered at this curve, the red curve, and the lower and upper bounds here are the standard deviations, okay? So we can see here there is a significant dispersion here. And if you zoom here in the low frequency, we can also see that we have a significant spread here, okay? For example, in this region, it's about 10 dBs, the dispersion. And this region is very near to the string fundamental frequency, okay? I mean, in frequency value and even in magnitude. So even although we didn't perform perceptual evaluations, my guess is that for sure we can perceive the difference here due to the variability. So as I said, perceptually different sounds may be produced due to the spectral variability, okay, observed in this region. So as conclusions of this part 2, I present you a framework, okay, for string musical instrument sound synthesis, in which we can include materials variability or even geometry variability. If we are working now on a parametric model of the guitar, so we can generate these uncertainties on the geometry as well and in the materials. So the effects of the variability of several spruce tone wood mechanical properties has been shown, okay, in the sound synthesis. The presence of such effects has been shown in the spectral domain, which suggests perceptual difference between sounds produced by nominally equal instruments. Actually, we have there are some works that have already investigated and have proved that nominally equal instruments generate different sounds, okay? But the interesting of this approach is that we can isolate variables here in order to investigate the influence of each uncertainty of each parameter uncertainty on the sound, okay? So more results very soon. We have an article on the review, okay? I will let you know by Cremona Lab News. I will send to Cremona Lab News as soon as possible our publication. Okay, so I just want to say a few words about the Urutau project. Okay, the Urutau platform is a cloud environment for design, analysis, and simulation of musical instruments. This is a project of the startup Turbonius, okay, founded by me and 3 other colleagues. And this project is in development, okay. So I'm gonna show you a video demonstration in which we consider a prototype here. a monochord, simplified instrument, okay? This monochord, of course, it has a single string, okay? So I'm gonna show you a short video here. So this is our monochord. This is the virtual environment, okay? So we have here the bridge, the peg, okay? So, oops, sorry. May I? Okay. So we can set many parameters, for example, the string. We can set also you can tune the frequency, for example. The plug position, we can choose, okay? Geometry parameters of the instrument, for example, the length, the width, the height. We can fit the neck parameters. We can choose the materials, for example, different options of woods, okay? And for the body, for example, the top plate, we can set the thickness of the top plate. Sides. The back plate. The peg, we can also adjust some position of the peg, the material. Finally, the bridge, the dimensions of the bridge. And the material. For example, spruce. Okay. And finally, the plug position. So we can run the simulation and you can create your profile where you can store all your different simulations and you can retrieve all the configurations, okay? And you can listen to the sounds, okay? From this different simulation. Okay, I think it's enough. So, as I said, this project is a project in development in the Turbonius startup. We also have the Shuri project, which is it's a web application for optimal treatment in small room acoustics. If you want to know more about these projects, or even if you are interested to collaborate, investments are very, very welcome as well. If you know someone which could be interested in this kind of project, okay? So, okay, thank you very much for your attention. Thank you, Sebastian, for the invitation, okay? It was a great pleasure to present for you, okay?
I think that the pleasure was ours. You're really working on the stuff we want to do, so
Oh,
I think we can
nice.
learn a lot from you. I mean, I have a lot of questions, but I don't know if anybody else on the audience has their own. Like, you can go ahead. I know Rafael has a lot of questions, but he's taking an exam now, so he cannot talk. Maybe I ask him to write down.
Okay.
So can you go into more detail how you're doing the simulation of this parametric simulation? It's you're doing like a FEM under, or what's
Yes,
the
of
engine of the cloud-based
the
simulation?
you mean from the stochastic approach? The
No, the last thing you showed, that moving the parameters of the instrument.
the monochord, you mean?
Yes, the monochord.
Yes. This is here. It's a solid neck here. Okay. We have a soundboard without fans. Okay.
Uh-huh.
We consider the air inside as well. So it's a fluid structure model, interaction model. Okay, here.
But
These
it's
are
a finite
plates.
element method, or
Yeah. This is a finite element method running behind all this front
okay.
end. Yeah. So
Well,
we. Sorry.
I
Go ahead.
think that, I mean, like our approach is to train a neural network with the FEM simulation. So after you can vary the parameters and just let the neural network to compute like all you're interested in.
Yeah.
I think in this
Yes.
case would be very easy.
Yeah. You mean we use here a parametric meshing? Okay. Is this the question?
Uh-huh. No,
So
yeah. I mean, that was the question. Like if you're actually doing the FEM simulation, or you are doing something else, like, I don't know, model order reduction or whatever.
no, do not. We don't do model reduction. Actually, this is an interesting approach for us because depending on the instrument, I mean, if we consider, I think, a complete guitar here and calculate all the modes, I think it will be costly, yeah. So a model reduction would be very interesting to be applied here.
Somebody else has any questions?
Yeah, I have a small question, even though I was able to join just at the half of the presentation, which was very interesting. So thank you. And my question was about the model of the simplified instrument that you used. And what do you mean by simplified instrument for the finite translation when you generate the sound? I was curious about the kind of instruments that you were using.
Okay. We use it a simplified instrument. I mean, it's a square plate guitar. It's only a square soundboard, okay, coupled to a single string, and it's applied free boundary conditions, okay. So the sides are 0.5 meters and the thickness 3 millimeters. So the focus here was just the influence of the mechanical properties, uncertainties on the sound, but the further steps we're gonna use a complete guitar. Yeah.
Okay, for this I have another question. So you say that the range was plus minus 10%, but from the table, yeah, I can see it's totally 10%. So I was wondering if you did, as you said, or just
Oh, sorry, it's
because
the sound it's cutting. I didn't understand because the sound is not so good.
Maybe you can write down, David. David is our like master student who just is looking for a.
Yeah, I will write it down. It's not very.
Yes, better.
So I was introducing David. Like, he's the master student who work on the artificial intelligence prediction of the FRF for like rectangular top plates.
Ah,
So
yes. Nice.
like we could directly fit these results into your model if you wanted.
Oh, nice. Yeah, please.
We don't hear you, David.
Yeah, I'm
You're
not.
muted.
Okay. Okay. So my question was quite easy. So I was seeing that in the table of viola that you showed us, the total variation is 10%. So I
Yes.
was wondering if
Oh, sorry, but I'm not listening.
It cuts. Maybe you want to write down the question and we read it out loud. Because your sound cuts after 3 seconds or so. In the meantime, Raffaele, who's a PhD student, the one we're doing the variation in the FRF with violin top plates, he asked if you have some plan of doing perceptual testing using your sound synthesis
Yes, of
methodology.
course. Perceptual, yeah. Actually, the main goal of my postdoctoral research is the focus is on the psychoacoustic studies using the physical model. Okay, so the last part of this research will be to perform perceptual studies. Okay, because actually I think it's the end of the process. Yeah, I think it's very important to study the influence of on the perception. Okay. Yeah, I can note that we have many topics in common here.
Yeah, we're very
When I
overlapped.
found actually it was Hannah that sent me your publication about violin and the property variation, property uncertainties on, I think it was in Nature Report. Yeah,
Scientific reports.
Scientific reports. Yes, sorry. And I found that was very interesting. And then actually it was, I have great interest on the work that you've done.
So I just put the link of the paper of David prediction of the FRF, so you can.
Nice.
Let me close the participants and put the chat. Okay.
Yeah, we also have the question by David now in the chat, if you want to read it out loud.
Yeah. He's asking if it was plus minus 10% or plus minus 5%, and the spread was...
No, plus minus 10%.
Okay. Great.
Can I make a small question? Hi.
Yeah, of course.
Hi. By the way, thanks for your nice talk. I have a question about the last your demo presentation you showed us about the computational complexity you need for determining the simulation and some information about the estimated time you need to compute the simulated.
Yes, that's a important point. We are using here cloud. We are using computers in the Google Cloud. Okay, so everything is implemented in the Google Cloud. So we use the processors of Google.
Mm-hmm.
For example, for a 3-second sound, I mean, we take about 1 minute, 1 minute and few seconds. Okay, and actually this depends on the complexity of our geometry, how many elements we're gonna have, okay? So, and we didn't still use computers of high performance, but in the future we want to parallelize the algorithms in order to obtain more quickly the simulations, okay?
I think neural networks is way faster.
Really?
It's
Nice.
1,000 that 10,000% speed up with respect to a
Oh,
FEM
nice.
simulation.
Good,
What
good.
software are you using for the FEM simulation?
Sorry?
What software are you using for the FEM simulation?
Okay. We use for the geometry, you use the Salome. It's a French software, open. Everything here was made with open source softwares, okay? So we use Salome Mecha for the geometry and for the mesh. And for the finite element analysis, we use the CodeAster solver, okay? And everything was implemented in CodeAster. CodeAster. I can write down for you. It's an open source software as well. And everything was connected and implemented using Python, okay?
Okay.
I will write for you here.
Yeah, because one thing I like about the neural network is that you can train on a paid software like COMSOL, and then the neural network that you obtain is like completely open source. So somehow you are like destroying the
Yeah.
business model of COMSOL.
Yes.
You don't
Yes.
need to do web simulations anymore. You just can like compute the neural network.
Yes. Yes. And actually, these softwares they are very good. They have a lot of tools that can be used. They are very well developed, but there are still several points that, for example, that we have in ANSYS and that we don't have in the CodeAster and Salome. So in the works I'm doing now, I'm using ANSYS. Go ahead, Mattia.
Yes, hello. First of all, thank you for the presentation. Very, your work is very interesting.
Thank you.
Your presentation was quite nice and exhaustive. I wanted to ask you to go back for a bit to the interaction between the strings and the body in the first part of the presentation. Because
Okay.
I didn't understand exactly how you implement the coupling. I wanted to ask whether
Okay.
you're using uh, the response of the bridge as let's say
Mhm.
to model the reflection at the bridge in the finite difference scheme simulation of the string,
Nice.
or
Uh-huh.
if you're doing something else.
Okay.
I didn't
So,
understand the specifics of the coupling of the implementation of the coupling force.
okay. So nice. So when you say reflection, um, okay. But here in this case, we do not use digital waveguides. Okay.
Okay,
So we are okay. So we don't have the reflection of the bridge, but we
okay.
have the interaction. It is described in the modal domain. Okay.
Mm-hmm.
So
Oh,
I can.
okay. Okay. Okay.
Okay.
Okay, no, no, no. I think I got it actually.
Yeah, it's a physical model in the time domain using a model approach. Okay, so
Okay.
we can describe the motion of these two structures by the superposition of their modes.
Okay.
And
I get it.
okay,
So basically, okay, so it's based on the model superposition. So you're
yeah,
basically a collection of oscillators. of this guitar.
Yes, it's not the
Okay.
actually I can show you here more details in this. So, for example, here for a simplified case, if I consider one string and one polarization, yeah, we're gonna have this representation. This is the coupling point, okay, at L, x equal L. So the displacement of the string can be described by the sum of these modes, which are the pinned end modes, okay, plus the interface mode, okay, which allows the coupling to the body. So
okay.
if we consider, for example, x equal L, we're gonna have ZS, okay, the displacement of the string at the coupling point, it's equal A0, okay? And the bridge displacement, I mean the body displacement, is the sum of their modes, okay? The superposition of their modes. So if we impose the displacement continuity at the coupling point, okay, and by writing down the string motion equations in the modal or domain, okay, here, for example, for the string motion, we consider the external force, which is the excitation, and the coupling force, okay, which the FC is unknown, okay.
Okay.
And for the bridge motion in the modal domain, we consider of course, it's the reaction of here of the coupling force. So you have also the FC. So making equal this, we impose the force continuity. So this from here we can use a finite difference scheme that allow us to compute this FC. Maybe it's not clear here, but it can be. You can find the details, the explanation in details, or we can discuss this after.
Okay, no, thank you. It was clear.
Okay.
Thank you.
No, okay, nice.
I didn't get this the first time around actually, but thanks for clearing up.
Okay.
Very, very interesting, very cool. Also, I wanted to say one more thing. This is not a question about the fact that we were struggling to get students participating and the fact that the exams are ongoing. I can confirm that one of the most relevant exams for for this talk is ongoing right now at this moment.
Oh, okay.
So, like
No,
the one
yes, no
where
problem.
we discuss sound synthesis, where we discuss physical modeling. Yeah, they're having the exam right now. So of course,
Okay.
we're just going to share the recording with them.
Okay, nice. Thank you.
Okay. Thanks a lot.
Okay, thank you, Mattia.
Cool. You met all pretty much our master students from this year. Oh, great. David asked for variations in the damping of the wood.
Ah, nice. I was.
And actually, what model are you using for the damping? That's something we all the
Yes,
time get from the review.
I was expecting to have this question. So actually, we perform our model considers the real body modes. Okay, we assume that the modes are real. So actually, we are performing here. It's an undamped model analysis. Okay, so we don't have a model damping factors here, so they are included after, and we impose a simplification actually. So we consider 2% to all body modes, but we are currently working on that in order to include kind of statistical and experimentally based damping factors. So actually this is a simplification, so we are considering 2% for all the damping factors.
Okay. Well, our neural network also doesn't have the damping factor at the moment, so
nice.
it's still an area to investigate and improve.
Oh, yes, because this problem of the damping factors, I think it's infinite, yeah. I think it's a very if you want to discuss the damping in structures and what kind of damping model we can use, proportional or non-proportional, of if you're gonna use real modes or complex modes, this is, you can have a lot of work to. That's actually, it's very interesting, this topic. Sorry, this
Yeah,
was okay. This, where can I read the message?
I can read it out loud for you if you want.
Oh, thank you,
Says,
please.
David says, I was wondering you could carry on the same investigation you performed for the elastic moduli with the orthotropic loss factors and see the effect.
Oh, yes, of course. The orthotropical loss factors, yeah, loss factors. Actually, we do not consider the loss factors here in our finite element model. Yeah, somehow they are related to the other mechanical properties, but yes, it's a interesting point to investigate by considering the loss factors of the wood. Okay, it's miss. Okay, so you're gonna include these loss factors?
probably. Yeah,
Yeah.
to work.
Okay, because yes, because you can see if we consider two equally nominally equal instruments, we're gonna see a high variability, yeah, in their dampings. And even if we consider different stages of the construction, and there are interesting results in the literature, yeah, showing that the variability of the damping factors is very, very high. Yeah. So it's a kind of, it's random. Everything is random.
Cool.
Nice.
Maybe final question. If anybody
Please.
has something else, I have just one last.
Okay.
Okay, Rafa asked like how much would be percentually relevant. Of course, we don't know. David enjoyed the talk about, and I think so. I mean, knowing our research, what would you like from us, if you could have something like?
Wow. I want investments to my startups.
Well, actually, no joke. Maybe Limi has some startup money. We could look into it.
Oh, nice. Nice.
I'm not very sure how it works, but we could try it. But in research terms, that's something that we actually can provide.
Nice. Okay, actually, I think we can keep in touch for many collaborations. For example, if you have a parametric model of, for example, of a guitar, we can connect it to my synthesis model, yeah, to this synthesis framework. It would be an interesting point to investigate the influence of the geometry variability, the geometry uncertainty, and see the influence on the sound production. Yeah. And actually, as I said, we have many points in common. Yeah, many research points in common. So for sure, I will write you. I will list all the things we could, yeah, we could work together and we could collaborate. and it
We
would
have
be
one.
very
Wait. Yes, we do have. I mean, we have variations for the Matthias thesis. It's about a guitar made with metamaterials with different geometries, and we
wow.
have the FRF for that. So
Oh,
if you
nice.
would be interested on them, we can
Yes.
share.
Nice. Okay, I want. Yeah.
Okay,
And
cool. Maybe you
so
can
you
make them
have
sound.
you have the FRFs and the modes as well?
Mattia.
Or
Yes.
it was
Yes,
okay.
Yeah.
but it's missing. Crucially, it's missing the coupling with the acoustic field, though.
No
I
problem.
couldn't
Yes.
manage that
Nice.
during my thesis.
And so you are working with metamaterials, is that? In
Yes.
musical instruments? Wow, nice. I think
Yes.
it's a promising subject, especially for musical instruments. It's very new, yeah.
Yes, and there's
So
very little work outside of. Yes.
they
Yeah,
are
nice.
ringing my bell. I come back in a minute.
Okay.
Ah. Okay,
So
but
yeah.
yeah, basically, I'll give you a rundown of what the metamaterial in this context consists of, and it's basically Sebastian together with researchers at Universidad de Chile found out via numerical simulations and then validated the results via experiments. And they found out that you can control the effective mechanical properties of thin wooden plates by carving periodical patterns of elliptical holes.
Wow.
Okay,
Okay.
so
Nice.
basically the idea of my thesis was to try to apply this to a complete instrument.
Nice. It sounds very, very interesting for me. And let's couple to the sound synthesis model maybe to
Yeah.
see the effects.
Yeah, it gets very complicated very fast, but yes, hopefully we can do it.
Okay. Oh, nice. And when you're gonna defend?
Next month,
Next month? Okay.
a little bit less than a month. Yes, I am. I
Okay,
have
so yeah.
basically my thesis is done, and I should submit it by Monday. So it's just it's the last stretch.
Okay.
Okay.
Oh, nice. Congrats.
Sebastian, I gave him a quick rundown of the metamaterials and what we were trying to do.
Yeah,
Yeah.
I'm gonna search.
We send you a draft paper because we're going to submit today or tomorrow. So
Okay. So
yeah, if you want to send us
Okay.
also the draft you have on the paper you submitted, we will be pleased to read.
Okay.
Great. I'm going to stop the recording here and just